The triangle ABC is right angled at C, the circle S has diameter AC, and the circle T has diameter CB. Draw a circle U which has diameter AB. So just what I've done is, if it has diameter AB, then to draw the circle you need to find the radius and you need to find the centre. So I just bisected this, I bisected the line AB and then just put the compass there to draw the circle U. So that's just how I did it there. No big problem at all. Now prove that in any right angled, it's a mistake there, that should be right angled triangle ABC, the area of the circle U equals the sum of the areas of the circles S and T. Okay, so it's a right angled triangle. Now if we look up here, so if the right angle is there, then AB is the hypotenuse. So it will be AB squared, the segment AB squared equals the segment AC squared plus the segment BC squared. So if we look at that, and that's fairly straightforward. Now, if it's an equation, so what is the area of the circle U? Well, the area of the circle U would, if we just kind of cut on down to the end here maybe, the area of any circle is pi times the radius squared. So what's the radius of this, what's the radius of the circle U? The radius of the circle U is AB, is AB divided by 2. So, and that'll be squared. And it's the same then for AC squared. So the area of that circle would be the segment AC over 2 squared plus pi times the segment BC over 2 all squared. So how are we going to use this to get to that? Well, if you were to multiply this out, you know, it's going to be pi times AB squared over 4, because 2 squared is 4, equals pi times the segment, that's AC squared. It's horrible eraser. AC squared over 4 plus pi times the segment BC squared over 4. So basically all we have to do to show that this can be written as that is just multiply both sides by pi over 4. And because it's an equation, if I multiply, as long as I do the same thing to both sides, I've not altered the truth or the validity of the equation. So that just kind of leaves you at that, and it's fine. That's it done. So if you multiply that by pi over 4, that will show you that this is essentially the same statement. And like that's the area of the circle U, and that's the area of the circle S, and that's the area of the circle T. So we'll let you ponder on that for a while. Now the next one then is, so I've kept this consistent with the marking scheme for those of you that might have looked at it. So the diagram shows the right angled triangle ABC and areas of the circle, or arcs of the circle ST and U. Each of these shaded areas in the diagram is called a lune, a crescent-shaped area bounded by arcs of the circle. Prove that the sum of the areas of the two shaded lunes is equal to the area of the triangle ABC. So I suppose we're looking for a statement of truth here. You're trying to show that one side can be written the same as the other side. So what I've done is I've just numbered these. It's similar to the marking scheme, but we're going to use this kind of thing. We know from the last part that if the area of the circle U equals the area of the circle S plus the area of the circle T, then half of the area of U will be equal to half of the area of S and T. Now let's look at, so here's the circle U. So if I write that a slightly different way, so if you look at circle U here, what have I got there? I've got, so what makes up the circle U there? It's A3, A4 and A5, so these three bits here. So A3 plus A4 plus A5. Now, equals a half. So what's the area of S? So looking at the circle S, so there's the circle S. Okay, so the area of the circle S is A1 and A4. So sorry, I don't need that half, so it's just A1 plus A4. And the area of the circle T is A2 plus A5. Now if we look at this, what have I got? I've got an A, I can subtract A4 from both sides. I can subtract A5 from both sides. And that leaves me with A3 equals A1 plus A2, which is exactly what I had to prove. So show that the area, so A3 is the right angle triangle, and A1 is these are the lunions. So done.